Good morning, dear students. Today we shall see the natural coordinates as the shape functions for CST element. In last class we derived the natural coordinates. The natural coordinates were found to be the area coordinates because L1 equals to A1 by A, L2 equals to A2 by A, and L3 equals to A3 by A. In previous class, we derived the natural coordinates L1, L2 and L3. They were found to be area coordinates. They represent area coordinates. Right? Therefore, L1 is unity at node 1. At the same node, L2 and L3 are zeros. L2 is unity at node 2. L1 and L3 are zeros at the same node. L3 is unity at node 3. And other two natural coordinates are zeros at the same node. This is what we have learned in the previous class. Right? Now, we shall see the natural coordinates. These natural coordinates as the shape functions. We can use the same natural coordinates as the shape functions. How it is possible? Let L1, L2 and L3 be the natural coordinates. Right? And N1, N2 and N3 be the shape functions. What is shape function? Shape function is an interpolating function. It is used to interpolate the unknown displacement field with nodal field variables. Nodal field variables. Okay. Now, for the considered CST element, we assume that the displacement is linear. Why? Because the CST element what we have considered is a linear displacement triangle. A linear displacement triangle. Therefore, the strain is constant. When the displacement is linear, it results in constant strain. Hence, it is named constant strain triangle, or you can say linear displacement triangle. Okay? For the CST element, you can assume a linear displacement model. Therefore, how we can assume here? We use this CST element for solving two-dimensional problems. Right? Therefore, if you take a point in the CST element, it has two displacements, u and v. The displacement u occurs in the direction of x-axis and v occurs in the direction of y-axis. U is a function of variables x and y and v is also a function of variables x and y. Understand? Where OXY is the reference frame. Clear? Right. Now, how you assume the linear displacement field? Here, how many components are there? Two components, u and v. Firstly, we take the displacement component u and see. U equals to alpha 1 L1 plus alpha 2 L2 plus alpha 3 L3. Or you can write, no problem. You can write u equals to say A L1 plus B L2 plus C L3. You can also write like this instead of alpha 1, alpha 2 and alpha. Okay. Where alpha 1, alpha 2 and alpha 3 are the generalized coordinates. Okay. What are L1, L2 and L3? They are the natural coordinates. Now my interest is to determine alpha 1, alpha 2 and alpha 3. Therefore, this expression I write in matrix form. The unknown displacement field U equals to a row matrix with L1, L2 and L3 into a column matrix with alpha 1, alpha 2 and alpha. Now I have to determine alpha 1, alpha 2 and alpha 3. Right? Now, At node 1, we know that L1 is unity and L2 is 0, L3 is 0. Okay? At node 1, L1 is unity, L2 is 0 and L3 is 0. Therefore, at node 1, with these conditions, what you can write? What you can write at node 1? U equals to U1, L1 equals to 1, L2 is 0 and L3 is 0. Therefore, you can write U1 equals to alpha 1. That is what you can write. Next, at node 2, U equals to U2 and L2 is unity, L1 is 0 and L3 is 0. Therefore, you can write U2 equals to alpha 2. Next, at node 3, this is node 3. Okay? This is node 1, this is node. At node 3, U equals to U3. Hence, U3 equals to, right? At node 3, L3 is 1, L2 is 0 and L3 is 0. If you substitute here, then what you get? U3 equals to alpha. We have 3 equations. These 3 equations we can represent in matrix form like this. Okay? From this you can determine alpha 1, alpha 2 and alpha. Alpha 1, alpha 2 and alpha 3. This matrix you can take. How? That we see now. Right? A matrix, a column matrix having the elements alpha 1, alpha 2 and alpha 3, which is noted by say alpha. It is a matrix of size 3 by, which equals to inverse of this matrix into a column matrix having U1, U2, U3. How you get this? You get from the previous one, this one. A column matrix having the elements alpha 1, alpha 2, alpha 3 equals to inverse of this matrix into a column matrix having the elements U1, U2 and U3. What are U1, U2 and U3? They are the nodal displacements of nodes 1, 2 and 3 in the direction of x-axis. Or you can define, they are the displacements of the nodes 1, 2 and 3 respectively in the direction of x-axis. Okay, they are the nodal displacements. Okay, right. Now, inverse of this matrix, you get again same into a column matrix having the elements U1, U2, U3. Understand? Observe here carefully. We have a CST element. We have a CST element. Right? And we assumed 3 shape functions N1, N2 and N3. N1 is unity at node 1 and it is 0 at the other nodes. Therefore, if you plot the variation of N1 on the CST element, you get like this. N1 is unity and N1 is 0 at node 2 and N1 is 0 at node 2. Like this. Understand? And similarly, you can plot showing the variation of N2 on the CST element as well for N3. Okay? N2 is unity at node 2 and it is 0 at node 1 and node 2. N3 is unity at node 3 and it is 0 at node 1 and node 2. Right? Okay. Now, U equals to again, first equation we take a row matrix with elements L1, L2 and L3 into a column matrix with elements alpha 1, alpha 2, alpha 3, but we have, the value of this matrix. That I substitute here. Okay? A row matrix having L1, L2, L3 into, in place of this column matrix, I write this. Okay? Now, again, we rewrite like this. A row matrix into. when you multiply these two, you get, again a column matrix with elements U1, U2 and U3. This if you multiply, right, how you get L1, U1 plus L2, U2 plus L3, U3. This is how you get. Right, this is for the unknown displacement field U. Okay. If N1, N2 and N3 are the shape functions, how do you write for the unknown displacement field U? U equals to N1 U1 plus N2 U2 plus N3 U3. This is how you can write. If you compare these two, what you understand? The natural coordinate L1 equals to N1. The natural coordinate L2 equals to N2. And the natural coordinate L3 equals to N3. Therefore, we can understand that the natural coordinates can be considered as the shape functions. The natural coordinates can be considered as the shape functions. What the natural coordinates represent? They represent area coordinates. Therefore, here the shape functions N1, N2 and L3 also represent the area coordinates. This is what we can understand. This is what we can understand. Understand? From this discussion, we can understand that the natural coordinates L1, L2 and L3 can be considered as shape functions. Therefore, L1 equals to N1, L2 equals to N2 and L3 equals to N. Clear? Sum of the natural coordinates is unity. Therefore, sum of the shape functions is also unity. Hence, N1 plus N2 plus N3 equals to 1. Here the shape functions represent the area coordinates. What is N1 therefore? N1 equals to A1 by A. Plus, what is N2? A2 by A. Plus, what is N3? A3 by A, which equals to 1. Because A1 plus A2 plus A3 equals to A. Understand? Right. Here, two of the shape functions are considered independent. And the third shape function will be considered dependent because sum of the shape functions is unity. If two of the shape functions are considered independent, right? The third shape function will be considered dependent because sum of the shape functions is unity. If I know N1 and N2, I can determine N3. Understand? So what we have learned in this particular class? We have learned that the natural coordinates can be used as shape functions. Right? And therefore the shape functions represent the area coordinates. Okay? And these shape functions are the linear functions. Hence the variation of each shape function over this CST element is linear. Because, let us see. If I take a CST element like this, with nodes 1, 2 and 3, N1 is unity at node 1 and it is 0 at node 2, 0 at node 3. Therefore, if you join, you get like this. The variation is linear. The reason is the displacement model is also linear displacement model. Right? And Now this figure represents the variation of the shape function n1 with respect to the area of the CST element. Okay, and the variation of the shape function n2 if you want, again I take a CST element like this. This is node 2, node 3, this is node 1. I get n2 is n2 unity at node, therefore I get this is 1. N2 is unity at node. And it is 0 at the other two nodes. And coming to the variation of the shape function n3, I take again a CST element like this. N3 is unity at node 3, therefore I get the variation like this. N3 is unity and it is 0 at other two nodes. Clear? Thank you very much.